Hello there, welcome back. Today we are going to move on and talk about segments and congruence. Hopefully you had a good handle on all those definitions that you took on the other day and now you're ready to move on. So we're first going to talk about the joke. Who doesn't love jokes? And who doesn't love math jokes? So let's first start with this one. Why was the math book sad? And I tried to find the saddest math book that I could possibly find on the internet, and this was possibly it. So why was the math book sad? If you didn't know, it's because he had so many problems. No, nothing? Okay. Well, let's move on anyway. So let's add a couple of definitions to the ones that we've already come up with the other day, which we had so many of. The first one being what a postulate or an axiom is. A postulate or axiom, essentially the same thing, is a rule that is accepted without proof. So I can just state it, and I don't need to show why that works or anything like that. I can just say that it is true, and we will accept it. Typically, it's a pretty self-explanatory and very simple proof, which is why we skip that step. However, we also have things called theorems. These guys are rules that can be proven, and we're going to prove some of them. We're going to do a little bit of proofs, more so in our next unit, but you did see one in the past, so hopefully moving forward now you have a better handle on what a proof is. But a theorem is a rule that can be proved or proven. So let's use our imagination. You are on a freshwater fishing trip, and you catch that fish below. Yay, good for you. By law, you must release any fish between 15 and 19 inches long, and you need to measure it. So you need to measure your fish, but the front of the roll on your boat is worn away due to years and years of you going out and fishing. So we need to figure out, can I keep this fish? So there's a couple of things that you want to ask yourself, okay? So is it possible to measure it without starting at 1? And really, yes you can. So let's say instead the head of the fish is at 4 inches. Okay, so what I mean by the head of the fish, that means the very front there, and I know it's not marked or anything like that. Let's do something nice and bright. Okay, so this part right here, that is at 4 inches. Okay, where do you see the tail of the fish at? Well, looking here, I can see it looks like it's about at 16 inches. Can I tell how long this fish is just by that information that's given to us? And the answer to that is yes, and we'll bring up a postulate that says that is so. So it doesn't matter that I'm starting at 1, I can still see how long it is based upon the fact that I know it's starting at 4 and it's going to 16. Okay, so the big question here is, can I keep that fish? Well, knowing that it's going from 4 to 16, you know that the length of it is 12. So based upon knowing here that if it's between 15 and 19, I have to throw it back, the good news is you can keep that fish. So this is the postulate that we use in order to show that that was going to be okay. Okay, so this is called the ruler postulate, and this is what allows us to use a ruler to measure things. Every point on a line can be paired with a real number. This makes a one-to-one correspondence between the points on the line and real numbers. The real number that corresponds to a point is also called a coordinate. Okay, so with that fish that we were talking about, the front of the fish, the very first point of it, was located on an actual number, which is why we're able to calculate the distance. The end of the fish also is on another number. The ruler postulate as a visual. I always love to give you visuals as well as the wording, because some people get the wording really well and some of you get the pictures really well. So what we can say is we want to find the distance from A to B. That's going to correspond to a specific coordinate, and we're just going to call it A and B for now. But on a ruler, that's actual numbers. And so what I can see is the distance AB. Now look at how we did the notation. Notation here, if I want to find the distance from A to B, I essentially am talking about a line or a line segment, but do you notice how I don't have anything above it? When I'm asking for distance, I'm going to just list the 2 letters I'm finding the distance between. Anyways, moving on. So here I'm looking for the distance from A to B. I'm going to do the absolute value of A minus B. And I want you to kind of think about that. Why on earth would I need to do the absolute value of that? And we're going to do an example really soon that's going to kind of highlight that difference there, okay, why we're actually doing that. So what I want you to think, though, is that we're going to do some segment addition. I want you to think of a couple scenarios. So the first scenario, you need to solve for a piece, or solve for the second scenario would be solving for the whole thing. So here are 2 examples to kind of think about how we would go about doing that. Our first one here. The distance from the lunchroom, which I know you all love to go to the library is approximately 30 feet. And then the distance from the library to the gym is approximately 50 feet. If you were walking from the lunchroom to the gym, about how many feet would you be going? So I just want you to kind of think about that. can I figure out how many feet it is altogether if I know those individual pieces? The second scenario is the distance from the main office to the band inquiry room is 60 feet. The distance from the main office to the guidance office, a little bit further down, for those of you who are not too familiar with that, it's a little bit further down, is 75 feet. How far are the band inquiry rooms from the guidance office? Is that something that we can figure out? And for both of these, the answer to that is yes. And what we're going to be using is the segment addition postulate. Ding, 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 here's a postulate, so that means we need to write it down in our notebooks. Write down what you need, whether it be the words or the picture or both. So the postulate, the segment addition postulate states, if B is between A and C, that's a really key word there, B is between A and C, meaning it's forming a straight line and they are collinear, then AB, remember the distance represented just two letters there, plus BC, again, that's another distance, equals the total of AC. So this is what we're going to be using to find the distance from the lunchroom to the gym. Because we can find the two individual pieces, then we're going to be able to put them together. So this part plus this part is totaling the whole thing here. So in other words, if AB plus BC is equal to AC, if this is given to you as a statement, then I automatically know that B has to be somewhere between A and C. I can't specify exactly where it is unless I know more information, but I know that it's somewhere between A and C. And so using this kind of idea here is what we're going to be doing, and that's how we found pieces of it, because I can tell you what AB is, and I can tell you what AC is. That was here would be the example from the main office to the band inquiry rooms, and this represents the distance from the main office to the guidance office, and I'm trying to find this piece. So we're still using the segment addition postulate. So let's look at a couple of examples using those two things. I want to find the measure of S to T. So I have taken ST and I've put it right up against a ruler, and I'm going to try to find its length. Okay. Now we discussed already that we have ST is absolute value of A minus B, or little a minus little big B, or whatever you want to call it. So A is located here at 2, and we see that B, which I'm sorry, it should be a little bit farther over, is about 5.4. And so now I'm going to do the absolute value of 2 minus 5.4. I'm substituting those values in. And when I subtract them, I get negative 3.4. When I take the absolute value, I get a positive 3.4. Because remember, absolute value represents the distance from 0. So my main question to you here is, why do we need to take the absolute value? Well, here's the answer to that. I cannot have a negative distance. You will never, ever, ever, ever get negative distance. So anytime you're doing these problems, then you make sure that you take the absolute value. Could you have done 5.4 minus 2? Yes, you could have, and you could avoid those negatives altogether. And that can happen in any case, where if I'm involving, you can switch numbers around, and that's fine. Make it easier on yourself. I like easy. I'm sure you like to make things easy, so on. Okay? All right, let's take a look at our second example here. I want to find the measure of xz. So looking at my diagram, I see xz represents this whole segment. So using that segment addition postulate, I know I like to put things in words first before I substitute some numbers in. That way I kind of have a good handle on what's going on. So xz represents the whole entire length. That is what my goals I'm searching for. I know it's made up of two parts. The first part is xy, and the second part is yz. So now that I kind of have a handle where I got two parts, 1, 2, equaling a whole, now I'm going to start substituting the numbers in. I don't know what xz is, but I know that xy is 23 and yz is 50. So from there, I know that xz is equal to 73. So now my question to you here is, if wy is equal to 30, can I use the segment addition postulate to find the distance between points w and z? Well, the big thing about the segment addition postulate is that that one point has to be between the two. So if I'm looking at that, is this y between w and z? And the answer to that is no. Can I find how far I would walk if I walk down to y and then I walk down to z? You sure can. But the actual distance between w and z is found right here between that. And as we have right now, this information and what you know about geometry, we cannot solve for that with that given information. So ultimately, the answer to this is no. W is not between x and z, and that should be w and z, so we cannot find the distance between w and z. All right, moving on here, we have point S is between R and T on segment RT. We want to find the lengths of RS and ST, and I'm giving you some information there on the left-hand side. Whenever I give you information and there's no picture to go with it, but you can sure draw one, I want you to draw one. It's always better to get a good visual. And nothing is going to be perfect. I am by no means an artist. Why do you think I use a PowerPoint? So putting in some things here, I've got my letters R and T with S somewhere between it. Does it have to be in the middle? No, but somewhere in the middle. I could have put it even closer over to this side if I really cared to do that, but I did not do that, so that's why I just chose to. Okay, so now I'm going to fill in the information I know. So I know between R and S, which is told to me right here, that length there is 2x plus 10. And the next thing I'm told is that ST is x minus 4, and now I'm told that the whole length RT is 21. And what my goal here is to figure out what is this value here and what is this value here. Well, since I have x's in there, I can't just subtract something from 21. I'm actually going to have to set up an equation and solve it. So the big thing here I know is that if I were to take RS and I added ST to it, I know that's going to represent the whole length of RT, and that's what I'm going to use to solve this. So what I'm going to do now is I'm going to set up an equation. Well, RS is represented by this. Now, in the past, it was just a number, but now we have a number with a variable, and that's fine. And then ST is going to be replaced with the x minus 4. I know these two things together equal RT, or in other words, this 21 right here. So now we're just solving an equation, and we've got to go think back to the days of Algebra 1, okay? We got to combine our like terms. So at 2x and x gives us 3x, 10 minus 4 is 6, and that equals 21. I'm going to subtract 6 and divide by 3 to get 5. So now my x value is equal to 5, but I still have not answered the question. Pay attention to the directions. I want actual values here. So what I'm going to do is take that and substitute it back into RS and ST and actually get values for that. So for RS I get 20 and ST I get 1. Now my original picture, does that look like it's got a piece of 20 and a piece of 1? It sure does not, but that does not matter. It's okay. Alright, so that's the big idea behind the segment addition postulate, and also utilizing the ruler postulate. Everything is one-to-one, so we can do this. The last couple things I want to touch on is the difference between some key words here, which is equals and congruence. We are going to be doing a lot when it comes to congruence, so we need to make sure we understand what that word means. When I say equal, it's something that you've already been familiar with. It's if I'm ever discussing measurement. So if I'm talking about the length, we're talking about miles, we're talking about inches, things like that, or even degrees. So length of a segment or the measure of an angle. Degrees and angle measures, lengths and degrees, those guys there, those are when we use equal signs. So 5 equals 5, 20 degrees equals 20 degrees. The measure of this angle is 30 degrees. If I'm using any kind of units, that's when we're going to be doing that, and we use the symbol that looks like the equal sign. The congruence information, this is a little bit tricky, tends to get a little bit confusing, and I understand that. This is when I'm discussing a relationship between the lines, angles, or our shapes. So because the lengths are equals, the actual shapes themselves are congruent. So knowing the lengths are equal, two lines are going to be congruent. Knowing the degrees are equal, two angles are going to be congruent. So on the left, we're really discussing numbers, but on the right, with congruence, we're discussing the actual shapes themselves, okay? The symbol is a little bit different. Look at the very top of the equal sign. We have this nice little squiggle on top. That represents congruence. So if I ever say this is congruent to that, you're going to use the equal sign with the squiggle. You'll most often use this, and we'll use letters, such as like segment AB is congruent to segment CD. Notice the notation here I'm using here, and we're doing values. While over here, if I do like x is equal to 4, that means the value of x is 4. Okay, or the measure of the angle is 220 degrees, its actual measurement there. That's why they are equal. So just to kind of finish things up a little bit, okay, with the congruence markings here, the first one is on a segment. Any kind of segments, we use these little tick marks that you see here. That's telling me the length of AB is equal to the length of BC, or in other words, segment AB is congruent to segment BC. When we can see this also on triangles. But when we talk about angles, we use these little arches here, okay? And as we talk about multiple ones, we include multiple more. Same thing with our distances on the things here. So this is equal to this. These two equal to these two there. Those guys are going to be congruent, but that does not mean that BC is congruent to AB. So that's the kind of important thing we want to get out of that, is if we have more than one marking, that's when we end up with different congruences. Our final example here would be this here. Using that same thing, I'm giving you some information about AB and BC. I want to know what's the length of AC. Well, given this, knowing that these two pieces are congruent, I'm going to set them equal to each other, and I'm going to solve for x. Okay, I hope this was a good basic. Oh, we want to take everything and put it back in. Sorry, I actually want to find the AC. I know that they're both going to, they're going to be the same length, so I'm going to take it and substitute it back in. BC is 66, so AC is 132.